Hello everyone. So today's class is very interesting. Yeah. So very simple also. So let us begin it and let me disclose you what we are going to study today. Okay, so this is what we are going to study today. And just to remind you what we have studied earlier, like what is a matrix, order of the matrix, types of matrices, notations, representation of the elements, and how to compare two matrices, addition, subtraction, multiplication of matrices, right? So now we are going to study what is transpose of a matrix, properties of transpose of the matrices, symmetric and skew-symmetric matrices, right? And some questions. So what is transpose of a matrix? So as you can see here, already I have written transpose of a matrix is a matrix which is obtained by changing rows to the corresponding columns and vice versa. So changing the rows of the matrix to the corresponding columns. So in that process, columns will also be changed to corresponding rows. Like for example, A is a matrix here. Then how to write transpose of any matrix? So notation of transpose of the matrix is A, we may write this small t. Okay, like just, yeah. So I mean this t, it stands for transpose, or you may write like this also. Okay, so one of these two notations you can apply. So A transpose is changing the rows to corresponding columns. 2, 3, 1. Then here 1, 7, 9. And you can observe here the first row becomes first column here. Second row becomes second column here. So this matrix is of order 2 by 3. Now you see the transpose of the matrix, it becomes 3 by 2. It is because the rows are changed to corresponding columns and columns are changed to corresponding rows. Okay, at the moment you change rows into corresponding columns, columns will automatically be changed. So you don't think about that. Okay, now you see, whenever we write any matrix A, Aij, order m by n. So transpose of the matrix can be represented like this, Aj. Okay, row index becomes column index here, and automatically column index will be, yeah, so row index like this. So order is n by m. Okay, so that is the basic thing. Now what are the properties of the transpose of the matrices? Okay, just okay. So first property, we can start with. First property is whenever we take transpose of A transpose, that is equal to A. Okay, so for example, if I write here any matrix A 1, 3, 5, 2, 7, 9. Now A transpose will be 1, 3, 5, 2, 7, 9. So let me take transpose of A transpose. So you observe the transpose of A, then take its transpose for this one. 1, 2, 3, 7, 5, 9. Can you see? You are getting the matrix A itself. Okay, so it is now verified. Second property is transpose of the sum of two matrices equal to sum of its transposes. So transpose of A plus B equal to A transpose plus B transpose. Third property is A minus B transpose of this is A transpose minus B transpose. We can verify. Fourth property. Okay, so A into B transpose of the product of two matrices equal to what here? B transpose into A transpose. Okay, so whenever we write transpose of AB, so please be sure A into B is defined. So what does it mean by saying A into B defined? Product of two matrices will be defined only when number of columns of the first matrix equal to number of rows of the second matrix. Okay, then only we can be able to multiply the two matrices. So transpose of A into B equal to B transpose into A transpose. Fifth property, that is, if we multiply any constant to the matrix and take its transpose, it is equal to K times A transpose. Okay, what is K? K is any constant, or you can say K is a scalar. Okay, so let us verify some of them. Okay, suppose, let me take example and verify. So here, suppose A matrix is, let me take some questions from NCERT. Okay, so 3, 4. So I'm taking question number 3, 3.3 exercise of NCERT textbook. You have A matrix is 3, 4, -1, 2, 0, 1. B matrix is -1, 2. Okay, so this is given A transpose. Yeah. B matrix is -1, 2, 1, 1, 2, 3. Okay, so we have to verify that transpose of A plus B equal to A transpose plus B transpose, and transpose of A minus B equal to A transpose minus B transpose. So here you can see, okay, A transpose is already given to us. So we can find A. Okay, so A is transpose of A transpose. That is 3 minus 1, 0. First column becomes first row here. 4, 2, 1. Okay, so B matrix is already given to us. So this is A transpose. This is B. We want A transpose and B transpose. Okay, let me find B transpose here. It is -1, 2, 1, first column, 1, 2, 3, second column. Okay, so if you write here A plus B transpose of this. So you can observe, be very careful here. This is A matrix, this is B matrix. So in order to add two matrices, no, the matrices should be of same order. So that is one checkpoint, right? Because usually students may ignore this, because it is A transpose given, right? So then if you want try to add also, no, you can't add. Okay, so you have to make it correction here. So A transpose is given. We can get A matrix by applying the property transpose of A transpose equal to A. So we are getting A matrix here. B matrix is already given. So A plus B, and we know how to add them. 3 minus 1 is 2, -1 plus 2 is 1, 0 plus 1 is 1, 4 plus 1, 5, 2 plus 2, 4, 1 plus 3, 4. Transpose of this. Okay, transpose of A plus B. Now here 2, 1, 1, 5, 4, 4. Okay, this is A plus B transpose. Now A transpose plus B transpose. So A transpose is given to us already. 3, 4, -1, 2, 0, 1. B transpose is here. So 3 minus 1, 2. Then 4 plus 1 is 5. Then here minus 1 plus 2, 1. 2 plus 2 is 4. Then 0 plus 1 is 1. 1 plus 3 is 4. Okay, so can you see here? So you can conclude from 1 and 2. Transpose of A plus B equal to A transpose plus B transpose. Verified. Okay, similarly, you can try A transpose minus B transpose also. So A transpose, sorry, minus B transpose, then you can see, yeah, so A transpose is already given to us. B transpose. Okay, 3 minus of minus 1, 4. 4 minus 1, 3. Then you see, okay, minus 1, minus 2, minus 3. Then here it is 2 minus of 2, 0. Third row is 0 minus 1, minus 1. This is minus 2. Okay, so minus 1, minus 2. Okay, now you can find A minus B, transpose of this. So transpose of A minus B. So A and, yeah, so here 3 minus of minus 1, 4. Okay, then you can see minus 1, minus 2, it is minus 3. 0 minus 1 is minus 1. Okay, then here it is 4 minus 1, 3. 2 minus 2, 0. 1 minus 3, minus 2. So 3, 0, minus 2. We have to take transpose. So 4 minus 3, minus 1. 3, 0, minus 2. Okay. So here you can check your A minus B. Transpose of this equal to A transpose minus B transpose. Okay, verified. So now we have verified how to take A transpose of transpose is A itself and these two properties. Okay, now one more question. We are given A matrix is 0, 1, 2, 0, 1, 2 column matrix. Okay, so B matrix is 1, 5, 7. Okay, so verify that transpose of AB equal to B transpose into A transpose. Okay. So whenever you find A into B, transpose of this, first you find A into B. So it means 0, 1, 2. You have to check whether multiplication is defined or not. 1, 5, 7. Okay, this is your 3 by 1 matrix, 1 by 3 matrix, right? So multiplication is possible. So here you can see R1, C1. Okay, 0 into 1, 0. Then R1, C2, 0. R1, C3, 0. Then R2, C1, 1, 5, 7. Then R3, C1, R3, C2, R3, C3. Okay. So this is A into B. Now if you write here, transpose of AB, it is 0, 0, 0, 1, 5, 7, 2, 10, 14. Right? This is your transpose of AB. Let me write it 1. Now B transpose into A transpose. So B transpose will be 1, 5, 7. A transpose, you can see A is 0, 1, 2, column matrix. Here it will be row matrix. Okay, so whenever you multiply this, you can see R1, C1, okay, R1, C2, 1, 2, 0, 5, 10, 0, 7, 14. Okay, so this is the matrix. Okay, so you can check here. So you are getting transpose of AB equal to B transpose into A transpose. Okay, so these are some of the properties of transpose of the matrices. Now, next one is symmetric matrix and skew-symmetric matrix. How do we define it? So symmetric matrix is basically a square matrix is said to be symmetric if and only if A transpose equal to A. So it means transpose of the matrix is equal to the matrix itself. For example, if I write here 2, 3, 5, you see what I am writing here? 4, 6. Okay, so here you see I am writing A matrix is like this. So if I want to write A transpose, it will be 1, 2, 3, 5. Now 3, 4, 6, 5, 6, 7. Okay, which is equal to A matrix. Okay, it means this one is called symmetric matrix. Okay, so here, yeah. So symmetric matrix is always a square matrix. A square matrix is said to be symmetric if and only if transpose of the matrix is equal to the matrix itself. And here you observe, so when transpose of the matrix will be equal to a matrix itself, you see, elements in the first row and first column, you are getting the same elements. Second row, second column, same elements. And third row, third column, we are getting the same elements. So without even finding, just by looking at the matrix, you can identify. Okay, whenever you see R1 equal to C1, R2 equal to C2, R3 equal to C3, it means the matrix is symmetric matrix. Okay. On the other hand, what is a skew-symmetric matrix? A square matrix is said to be skew-symmetric if and only if A transpose equal to minus A. It means transpose of the matrix equal to negative of that matrix. Okay. For example, you see what I am writing here. Okay, you just observe. I am writing here 0, 2, 3. Okay. Then I'm writing here minus 2, 0. Something I want to write here. Let me write here 1. Okay. Or let me write here is 1. Now I am writing here 0. Okay. Now here I am writing. Okay. What should I write here? Let me write 1 here. Okay, now 0, 2, 3. Here I should write minus 3. I will tell you why. And here it is minus 1. Okay, so could you observe while writing, I was taking a pause and writing that. And you can observe 0, 0, 0. Okay, I didn't take any matrix. I had to give a pause. Like here you can see I was writing 1. Then I changed it to minus 3. Okay, why it is like this? So, okay, so let's see first. A transpose equal to 0, 2, 3. Okay, then second row here, minus 2, 0, 1, it becomes second column. And minus 3, minus 1, 0. Okay, if you observe here, you see 0, 2, 3, 0, minus 2, minus 3. minus 2 0 1 2 0 minus 1 minus 3 minus 1 0 3 1 0. It means it is exactly negative of A. Okay, A transpose equal to minus of A. So here A is your skew-symmetric matrix. Okay, A is skew-symmetric. So the square matrix is skew-symmetric if transpose of the matrix equal to negative of the matrix itself. One more thing you can observe here, whenever we take any skew-symmetric matrix, diagonal elements are zeros. Okay, that is one of the important properties, or just to identify whether it is skew-symmetric or not, we can identify by looking at this 0 0 0, I mean diagonal elements. Second thing you can observe, here 2 3 1, here minus 2 minus 3 minus 1. It means elements of the upper diagonal and the lower diagonal, the corresponding elements are of opposite sign. If 2 here, it is minus 2, 3, minus 3, 1, minus 1. And whenever we are changing it, no, we are getting like this. So that we are getting A transpose equal to minus of A. Okay. So while identifying skew-symmetric matrix, or just by inspection, just by looking at the matrix, you can say whether it is skew-symmetric or not. First characteristic is diagonal elements are zeros. Second one is elements in the upper and lower diagonal, the corresponding elements are of opposite sign. Okay, so opposite sign may be clear because we have to take A transpose equal to minus A. But why the diagonal elements are zeros? Let me tell you that. Okay, so it is one of the, you can say, question you may get in 2 marks. Yeah. So prove that the diagonal elements of a skew-symmetric matrix are zeros. Okay, so let A be a skew-symmetric matrix. A be a skew-symmetric matrix. It means A transpose equal to minus A. Okay, because it is skew-symmetric. If I write here A equal to Aij order m by m, because skew-symmetric matrices are square matrices. Okay. Now here, yeah, you can say for diagonal elements, the matrix has to be square matrix. Okay, the diagonal element concept exists in square matrices only. So A equal to this. So here you see A transpose equal to Aj. Okay, order m by m. Now we are having A transpose equal to minus A. Now we can compare the corresponding elements. So Aij equal to minus of Aji. Okay, is it clear? Now we are talking about diagonal elements. For diagonal elements, I equal to j. Is it clear? So why I equal to j? Because diagonal elements means A11, A22, A33. So 1, 1, 2, 2, 3, 3 means row index equal to column index. Okay. So it means I equal to j. So that gives us Aii equal to minus of Aii. Or you may write Ajj equal to minus of Ajj. Or you write 2Aii equal to 0. Or you write Aii equal to 0. Okay. So it means diagonal elements are zeros. Diagonal elements. Okay. So So another important property, prove that for every square matrix A plus A transpose is a symmetric matrix and A minus A transpose is a skew-symmetric matrix. Okay, for every square matrix. So we have to prove it in general. So whenever you have to prove any matrix is symmetric matrix, what should you do? You have to take transpose of the matrix equal to the matrix itself, right? So when we have to prove A plus A transpose is symmetric, it means transpose of A plus A transpose is equal to A plus A transpose. Okay, we are given, okay, let P equal to A plus A transpose. Okay, I'm writing like this. So you can write, as I said, this notation or this notation for transpose. Okay, we are given A is a square matrix. In fact, it is any square matrix, 2 by 2 or 3 by 3. Okay, we are studying up to 3 by 3. Okay, P equal to this. So it means we have to prove P is a symmetric matrix. So let us take symmetric means it has to be like the matrix has to be equal to its transpose. So P transpose means transpose of A plus A transpose. Okay, and we know transpose of A plus B equal to A transpose plus B transpose. It is one of the properties. So here A transpose plus transpose of A transpose. And we also know transpose of A transpose is A itself. So A transpose plus A. That is equal to A plus A transpose. Matrix addition is commutative. So you are getting, it is P. The P transpose equal to P. P transpose equal to P. Or you can say A plus A transpose. Okay, so transpose of this equal to A plus A transpose. Okay, so this implies A plus A transpose is a symmetric matrix. Symmetric matrix. Okay, now let us prove. This is the first part. Second part is A minus A transpose. It's skew-symmetric. We have to prove. So we can take let Q equal to A minus A transpose. We have to prove it is skew-symmetric. So whenever we have to prove any matrix is skew-symmetric, so we have to prove transpose of that matrix equal to the negative of the matrix itself. A transpose equal to minus A. Okay, this means A is a skew-symmetric matrix. So let us take Q equal to this. So here we have to prove Q is a skew-symmetric matrix. So Q transpose, that is transpose of A minus A transpose minus transpose of A transpose. It is because, as we know, transpose of A minus B is A transpose minus B transpose. So A transpose minus of A. Again, using this property, transpose of A transpose is equal to A. So it is A transpose minus A, which is minus of A minus A transpose, means we are getting minus Q. Okay. So we have Q transpose equal to this, or you can say transpose of A minus A transpose is minus of A minus A transpose. Okay. Means transpose of A equal to minus of A criteria. Okay, it is in the form of A transpose equal to minus of A. So this implies A minus A transpose is skew-symmetric. Okay, it is just skew-symmetric matrix. So whenever you have to prove any matrix is symmetric, you have to prove transpose of the matrix equal to the matrix itself. Whenever you have to prove the matrix is skew-symmetric, you have to prove transpose of the matrix equal to negative of the matrix. Okay. Third part and last part is prove that A plus any matrix A, any square matrix A can be expressed as the sum of a symmetric and a skew-symmetric matrix. Okay. So now we have proved for any square matrix, A plus A transpose is symmetric. Okay. And we also have proved A minus A transpose is skew-symmetric. Okay, just now we have proved it. So it means if I write here half of A plus A transpose, it will be symmetric, right? By multiplying any constant will not change the property of symmetric or skew-symmetric. Okay, similarly, if I write here half of A minus A transpose, it will be skew-symmetric. Okay, so yeah, if we multiply, so again here you can say it can be skew-symmetric because the properties will remain intact. The diagonal elements are 0, 0, 0, right? Yeah, 0, 0, like that, depending upon 2 by 2 or 3 by 3 we are taking. And upper diagonal and lower diagonal elements, that opposite sign, even if you multiply half, so it will not be changing. Now, can we write? We can write A equal to half of A plus A transpose plus half of A minus A transpose. Can we write like this? You can check it. See, if I look at right hand side, half A plus half A transpose plus half A minus half A transpose. So half A transpose minus half A transpose is getting cancelled. Half A plus half A. So A equal to A. So any matrix A, any square matrix A can be written like this. So as we just proved, this is symmetric and this is skew-symmetric. We can declare A can be expressed as the sum of, hence we can say A can be a square matrix. I can write here a square matrix A can be expressed as the sum of a symmetric and a skew-symmetric matrix. Okay, so I think we have to wind up the class now, and next class will come with the questions based on this concept and beyond that. Okay, so thank you so much.